Have you ever found yourself surrounded by a sea of points, trying to figure out which one has the most neighbors? It can be quite the puzzle. If you're facing this challenge, you're in the right place. Today, we're diving into how to find the densest point in a set of points. I totally get it. Trying to find the point with the most surrounding points can feel overwhelming, especially when you're dealing with a large data set. You're not alone in this. Many people encounter similar issues when working with spatial data. Let's look at a specific example. One user asked, "How can I find the point with the most surrounding points within a certain radius?" They provided a set of points and wanted to identify the densest point function. Sound familiar? If so, let's explore this together. So, what exactly is the densest point function? It's about finding a point that has the highest number of neighboring points within a defined radius, whether that's a circle or a square. This can be tricky, especially with densely packed points. And stick around. By the end of this video, you'll have a solid understanding of how to implement a solution for this problem, and I promise it will be worth your time. To find the point with the most surrounding points, the user should first implement a two-dimensional range tree. This data structure will allow efficient querying of points within a specified range. Next, the user needs to implement a range counting query. This query will count how many points fall within a specified radius around each point in the dataset. After that, the user should iterate through each point in the dataset. For each point, they will call the range counting query to determine how many surrounding points exist. Finally, the user should compare the counts obtained from the previous step. The point with the highest count will be the densest point, which is the solution to the problem. Fun fact, did you know that the concept of range trees was first introduced in the 1980s? They have come a long way since then and are now essential in computational geometry. Now, let's look at the answers provided by other users. Now here's the refined question. Are there any libraries available that implement 2D range trees with fractional cascading? This could save you from reinventing the wheel. And there you have it. You now have a clearer path to finding the densest point in your dataset. Remember, using efficient data structures can save you a lot of time and effort. If you found this video helpful, don't forget to subscribe for more tips and tricks. An alternative approach suggests using the plane sweep algorithm for more efficient point selection. This method simplifies the problem by allowing one-dimensional range queries instead of two-dimensional ones. The user outlines steps to implement this algorithm, including sorting points, managing pointers for insertion and removal, and using a tree structure to count surrounding points. This method achieves a time complexity of O(n) log n. For circular neighborhoods, the user suggests approximating the circle with rectangles, allowing for easier counting and management of points. This can also be optimized by using horizontal slices. That's all for that response. Let's see what someone else had to say. An alternative approach suggests using a KD tree to efficiently find the point with the most surrounding points. The idea is to create a tree where each node contains information about its descendants and their count. During the search, you check if the bounding box of a node is within a certain radius of the current point. If it is, you can add the count of that node's descendants to your total. This way, you avoid checking every point individually. Let's move forward and look at another answer. An alternative approach to finding the point with the most surrounding points involves pre-processing your data. First, create a grid with cells sized according to your radius. Then, for each point, determine which cell it belongs to. This allows you to quickly estimate the number of neighboring points. For each point in the grid, you can calculate the number of neighbors by checking the surrounding cells. Once you have these estimates, you can use a max heap to efficiently find the point with the most neighbors. This method significantly reduces the number of expensive checks needed, especially if you use a finer grid for better estimates. It combines efficiency with accuracy, making it a strong alternative solution.